This happens only once in 16 years.
It will be so close to the black hole that the speed of it will reach almost 3% of the speed of light.
I said, my wife, I have to tell you something. It's really there.
Since Einstein published his theory of general relativity in 1915, scientists have embarked on a 100-year crusade to prove him right. In pursuit of this goal, ESO has been training its telescopes on a hidden monster in the heart of the Milky Way for over a quarter of a century. This cosmic colossus is a supermassive black hole, 4 million times the mass of the Sun. Now, after an epic 26-year observing campaign, the effects of Einstein's general relativity have been clearly seen for the first time around this supermassive black hole. However, astronomers aren't only interested in finding out if Einstein was right. They also want to use these measurements to test our most fundamental understanding of the universe.
I understand this is something Einstein predicted.
Yep.
How long ago?
Yeah, 100 years ago this year, in 1916. This is a huge discovery, not only confirming Einstein's ideas, but opening a whole new way of exploring the universe.
So is he even, does he seem even smarter now than he used to seem?
He's like so up there that there is no getting smarter. It's like infinity. It's
But
like
you
going
guys-
further north than the North Pole. You know, it's just like...
How do you prove a black hole? How do you know those gravitational waves proved the collision of two black holes?
Somehow, eventually, they are able to observe phenomena.
No, they can't observe. It's too far away. It's too theoretical. How do we know what they're saying is true? You know what it really is? It's all science fiction.
So does that make you a skeptic?
You have never met someone at a place unless it was also at a time. You have never met someone at a time unless it was...
Okay, I get.
So we...
Well, wait a minute. What happens to a photon from 13.8 billion years that comes this way and enters my eye so I can see it? Why? Where's space involved in that?
It entered your eye at a time and at a place, right here. That's all that matters here.
Is that all we're saying?
Well, once you have formalized space and time and know that they're conjoined, then you can make all kinds of fascinating calculations.
Well,
with
what is all
relativity.
that? The train's going and I'm walking down there.
Yeah,
I'm walking down the train. I'm walking on the air.
And the time
and the thing,
change.
and the change. What is all that?
That's all the consequences of thinking about space and time as conjoined.
But it's confusing.
So,
wait a minute. Not only is it...
the universe is under no obligation to make sense to William Shatner, okay?
No, but William Shatner's under the obligation to make sense of the universe. Why do I slow down as I approach the speed of light? It doesn't apply to a photon 13.
Now you want to freak out? I don't want your head to explode. You ready?
Yeah.
Okay? No, you're not ready. Are you ready?
No, I'm ready. I'm ready.
As you approach the speed of light, time continues to slow down.
Yes.
At the speed of light, time stops. Which means for a photon moving at the speed of light, when it is absorbed in your retina, it is the same instant it was emitted at the Big Bang 14 billion years ago.
That's what I thought.
The photon gets emitted, bam, it's in your, as far as it's concerned, it is in your eye in that same
Can
instant.
we measure that photon and
Yes.
observe the Big Bang?
I know that came from the Big Bang, and I'm watching it, and it's taken 13.8 billion years to reach you, but if you are that photon, it does not experience that time delay.
What a great science fiction story that is.
Instantaneous. so I mean, it's science fiction, all right?
Okay.
But we know about wormholes. We know the mathematics of them. We don't know how to make one yet, and plus they're kind of unstable, and if you go in, they might collapse. So you have to, that's the science fiction part of it. There's a wormhole sitting there allowing people to leave Earth and travel much shorter amounts of time to go to another part of the galaxy.
And the difference between a wormhole and a black hole?
Well, so if you're near a very strong source of gravity, from Einstein's relativity, we know that time ticks more slowly for you than it would elsewhere. So if you're near a black hole, weird things go on, and they captured much of this in the film. One of the executive producers of Interstellar is a professor of physics at Caltech, and his name is Kip Thorne. By the way, one of the robots in the movie was called Kip. So coincidence? I don't know.
What's the difference between a black hole and a wormhole?
So a black hole, you fall in and you're not coming out ever. All right. A wormhole has a lot of the similar physics to a black hole, except it's a portal to another place in the galaxy. And so you can use it in principle to travel great distances much faster than if you otherwise sort of took the detour. And in Star Trek, they kind of do that with their warp drives. They warp space, and they can travel much. Well, at the time they didn't have that vocabulary, and if they did, that's surely what they would have called it.
There was a golden age in which we solved most of the major problems in black hole theory. This was before there was any observational evidence for black holes.
Set against a backdrop of bright gas, the black hole's massive gravitational pull bends light into a ring. However, this isn't a real photograph, but a computer graphic rendering, an artistic interpretation of what a black hole might look like. 100 years ago, Albert Einstein first published his theory of general relativity. In the years since then, scientists have provided a lot of evidence in support of it. But one thing predicted from this theory, black holes, still have not been directly observed. We've never actually taken a picture of one before. However, you might be surprised to know that it may soon change. Getting this first picture will come down to an international team of scientists, an Earth-sized telescope, and an algorithm that puts together the final picture.
This is the first ever image of a black hole, released by the Event Horizon Telescope collaboration on April 10th, 2019. It shows plasma orbiting the supermassive black hole at the center of the galaxy M87. The bright region shows where plasma is coming towards us, and since it's traveling near the speed of light, it appears brighter when coming towards us and dimmer when going away. This is called relativistic beaming. From the images, scientists can tell that the plasma is orbiting clockwise. It takes around 2 days for the plasma to complete one orbit. Here, we are looking at the black hole using electromagnetic waves with a wavelength of 1.3 millimeters. But let's have a look at what we would see if we were looking at different orientations. The warping of space-time around the black hole means we can see light even from parts of the accretion disk behind the black hole. They are lensed above and below the shadow region. Why is the image so fuzzy? The answer is because it's so tiny. Don't get me wrong, the black hole itself is huge, supermassive, in fact. As measured from this picture, the black hole has a mass 6.5 billion times that of our sun. The actual size of its shadow is nearly the size of our solar system. But located 53.5 million light years away, its size from our perspective is only about 40 micro arcseconds. That's the angle it makes on the sky.